Okay, so what's the advantage? Okay, what's the advantage of having code? What is it that having code could do that CFC cannot do or parity cannot do? It can define which bit has the error, and so it allows for correction. Otherwise, with most of the other systems, it just tells you there's an error, especially with CRC, but doesn't tell you which bit actually has the error. And what's the disadvantage of parity, normal parity systems? What's the problem with parity error detection system? Pardon? It cannot detect if the error involves more than one bit. This is a parity system. That's not necessarily correct. You know what's wrong with the parity error detection system? It cannot detect 2 errors in a byte. How about 3? How about 4? Okay, can you tell me what's wrong with the parity error detection system?
There are even number of errors in the frame of the message, the message.
Almost there. You corrected one part, but you made a mistake in the other part. Say again?
It cannot detect an even number of bits.
It cannot detect an even number of bits, not just 2 or 4 or 6 or 8, but not in the message. Only in one, no, not in the frame.
Again, for frame, I meant like the different sections of the message.
But it's a byte. No, only in one byte. Okay, so maybe if in the exam you don't say in a byte, don't get the mark for it. Not in the entire message or the frame. Okay. And what is the binary representation of the polynomial x to the power of 2 plus 1? Now the polynomial generator x squared plus 1. What would that be in binary? 1, 2. 1, 0, 1. Yeah. Exactly. You need to know how to convert from polynomial to binary, and you don't need to do it vice versa, but you should know automatically. Right, the checksum. Maybe we mentioned it, we'll go through it again one more time. If you get the frame, it's basically you're adding all the bytes one after the other, and whatever the sum you have at the end, we send it, but we work out the complement. We complement it and we send it. So the idea is that if you add them again, you'll get a 0. If you add them all again, you get a 0. But okay, there's a point that you need to check it yourself. But okay, so we'll take this example. You add the first byte, this byte here, which is this, plus that one there, put it there, and you do a binary adding. Okay, this is the point I want you to be careful with. Sometimes when you add them, there is an overflow, and sometimes there is no overflow. If there is an overflow, in some textbook, they say that's the one you put there and you add. You don't always add one as in the complement, so double check that. So you add 0 plus 0 is 0, and this is binary, simple binary adding. So 1 plus 0 is 1, 0 plus 0 is 0, 1 plus 0 is 1. But when you get to 1 plus 1 is 2, and 2 in binary is 1, 0. So you put the 0 and you write the 1 on the other side. On the next column, you carry to the next column. So you have 1 plus 0 plus 1, that's another 2. You put the 0 and the 1 is put on this side. So 1 plus 1 is plus 1, that's 3. In binary, 3 is written 1, 1. That's how you write binary in 3, 1, 1. So we write the 1 here, and the other one that goes in here, in the textbook says, okay, you can't have it there, but add it to this one. So you don't always add 1, you only add 1 if there's an overflow. If there's a 1 carried, then you add it to the rest of the byte. So in this case here, 0 plus 1 is 1, and the rest of the numbers, they just add it to nothing. So now we've just added those two, and that's the result. So now we add that result to the third byte, which is this one here. So we add this plus this. So 1 plus 0 is 1, 1, 0 plus 0 is 0, 1 plus 0 is 1, 1, 0 plus 1 is 1, 1. It's only the last one. 1 plus 1 is 2. A 2 is written in binary is 1 and a 0. So we write the 0 and the 1 is written here. It's overflow, we move it down there and we add it to the byte. If there is no overflow, then there's no addition. And when you finish, this is the final result. Before you send it out, flip every bit. So every 0 goes into 1, every 1 goes into 0, and that is the final sum that we put at the end of the frame. This is a very fast operation, and it seems to work. And they use it in TCP, but only to check the header. They don't do it on the entire data. They only do it to check the header of the segment. Now, imagine if we received this. The sender sent us this frame. In the checksum, that last byte now is used to check is this correct or not. In fact, if you add all this with this byte, you should get zeros at the very end. They are the complement to full 1, 1, 1, 1, 1. So let's see if it actually works. So here's the same information is being received. So here's exactly the same example, the same frame. We received those 3 bytes, and that's the last byte that was appended at the end. That's the checksum. So let's see if it works. So the receiver will also add this plus this plus this, and keep adding them. This plus that, you get a result, add it to that, you get a result, add it to that until the end. So the first 2 bytes are pretty much the same. So we add that and that. And if there's an overflow, we put it there and we add it. If there's no overflow, you don't have to add the 1. So now we have that byte with 1, then we add this byte. So that's the result. Now we add it to the third byte, which is that one there. The result of the first 2 plus the third byte, we add them up. And there's also an overflow here. See, 1 plus 1 is 2, 0, 1, and the 1 we put it down there. And we add it. Now, that's the result of adding those 3. We're going to add that result to this last byte. That last byte is not data, so you need to know that's not a data. Now we take that and we add it to the last byte. So if you add them all, they're all 1s. We do the last step, flip everything, and they're all flipped, and that's all 0s. And if they're all 0s, that means most likely there's no error. Now that's the operation of the checksum. Just wanted to go over it